on the rotation of the year. Right? So we are going to, after I upgrade my MacBook, I cannot use the dashboard. There's no more dashboard on the MacBook, so I cannot see the calendar. There might be way it's lazy to find. So our Thanksgiving is the 28th. So that's a Thursday. We are going to have a class on Monday, 25. Then I'm going to cancel the class on Wednesday, 27. I don't think it's officially holiday, UB campus. Is it off day, 25, Wednesday? I don't think so.
25 is Monday, right?
It's a Wednesday.
25 is Monday, 27 is
Oh.
Wednesday.
The 25 is Monday, 27 I mean. But anyway, we are not going to have a class, 27, okay? But we have class 27 Wednesday. But anyway, so we are not going to have class the day before the Thanksgiving, so you can enjoy the holiday. And but the other schedule will be going on, so please complete the project as well as the missing homework, and also we are going to have the final exam. I need to check the final exam schedule, but the result is assigned based on the class the schedule. So mostly it is either Monday or Wednesday, 8 a.m. or the 10 a.m. It depends, so I will let you know. Okay, so we did the database design, and then we are able to create a database using the DBMS. So in the practice, we are using MySQL database. MySQL is one of the popular relational database management system. But go back to the very basic fundamental of the why we are using database system. Why? Why we are using database? Always think about your laptop. Is there anyone who are using the DBMS for individual purpose? Nobody. Even though CEO of Oracle, they don't use it. He doesn't use the Oracle database for personal purpose. Then why the people are using the DBMS, database management system? Why? It's a large data. So since we have the very large data, so when we are talking about the large or the big data, how much large, how much big, it depends. Depends on what? You mostly computer capacity, like the CPU processing power and the memory power and the storage, the price and the speed like that. So, but a long time ago, like the end of the 60s and the beginning of 70, when the Dr. E.F. Code thought about the new model to make the very large data. So even the megabyte is a huge data. So he cannot put all the data on memory. So when you are doing any programming, definitely there's absolutely no programming without data. So no matter what programming you are using, like even the print, the hello world. When you print the hello world in Python, hello world itself is the data, right? So definitely you should have the data, but mostly the data will be memory. So memory-based data management. So we can use a memory-based data management. No matter what application you are using on the laptop, it's on the memory, then synchronized to the file system. That's what's going on. Then why we need? So because it's very large, it's really large. So when we have a large amount of data, what is the most problem? Serious problem. Speed. Okay? So the reason why we keep manage such a data is to use. If you are not going to use, you don't have to have such a data. Even archived data, sometimes you need to keep the 5 years for the banking transaction because it's a policy. Okay, it's a rule by the federal or something like that. Even though you never access the previous one, we need to keep. So because just in case we need to access such a data. When we find such a data, it should be fast. If slow, the Like for example, the Amazon, they said that if the query time is increased by the 100 millisecond in Amazon, then they said that I'm not sure, but they said in their report, they lose 1% of the revenue. If the query response time is increased by the 100 millisecond, it's the 100 millisecond, they lose the 1% of the entire. 1% of Amazon is huge, really huge. So they lose the 1% of the revenue. So, which means the query response time to access data is very important. So, then the DBMS provide the fast, efficient, the method to access the data. Is it true? Actually not. Because DBMS itself is the software. We need to run the software and we need to manage the software. It's overhead. So without the DBMS, actually it's much, much simpler. So think about your C or the Java programming. For example, Java programming, you can use the file stream class, then open the file and write the data or read the data, close it. That's pretty much enough. Then it will be okay. But when you have a very large amount of data, it's not that fast. So that is a problem. So then why? It's the same problem when you are using the DBMS system. If you, no matter what database design model you use, so it will be eventually slow because you have a bunch of huge the amount of the resource used by the DBMS. Then how can the DBMS speed up to access the data? So one is query optimizer, because when we access the data, a bunch of different ways to find the data. So we can optimize. So we will discuss about that query optimizer next week. And another way, you can use index. So index is a different data structure from the data file or any file. Okay, most of the file is a heap file or just a file, which means it's non-ordered. Even though we have ordered file, so binary search cannot provide the huge. It's better than the linear, but the low band is still the more data you have, the longer time it takes. So there might be limitations. So we can consider the index. That is the last week, the topic indexing, the index structure. Then any other way? Memory. So always we are using, whenever we have a problem of the speed. So not only database, any data computer application, we are using cache. Even hardware design, if your computer is slow, CPU is not fast enough, you can use cache. Add to cache. There are different layers nowadays of the add to cache, right? You can quickly check. The bigger the better, so the bigger the cache you have, more higher complexity. So, but we have more and more such a cache. From the persistent storage, the memory, even though there is a cache on the hard disk, right, or the SSD, file system cache. Then we have the memory, even between the memory and the CPU register, there are several layers of the cache. So using cache, we can speed up. These are the ways to speed up to access the data. Are they enough? If think about data itself is not well organized, right? Not well organized. Even though you have the very fast cache or the optimizer, but it will take a longer time. So today we are going to talk about how can we make our database design better. Better means what? When we are using such the database, should be fast. Okay, let's think about the very basic question. Which one is better? The database is the data. So all students have the UBID. The other group of students, they do not have the UBID. Which group will be the better to find the specific student? Definitely the first one that who have the ID. Why?
Because there is unique one.
Yes, unique. If we have such a unique data, unique value, unique attribute or color, so it's easy to find. So even we can make the index, we can. So when we talk about the better, I said the better quality of database design, there are a bunch of different ways. Even though I give the same question for your midterm, so answers are vary. Okay? Even though I tried my best to standardize, but it's vary. That's true. But the sum of the database design is good for such a accessing the data. The other one is not. So, in other words, when we talk about the good database design or better database design, so that is the same problem as whether data are unique or not. In other words, redundant data or not. So, database designer or architect or even the programmer, they really hate redundant information. Why? If you have redundant information, which means it's not unique, it will be harder and harder to find the specific data. We cannot get the benefit of index. We cannot get the benefit of binary search. We cannot sort the data. Even though we sort the data, we need to check each and every one. So that is the reason that always we are fighting with the redundant information. In other words, since the database, so that is the reason we focus on a lot, the half of the semester to design the better and better. In other words, we try to eliminate, if possible, think about the relational database model. So what is a relation? It's a group of data, but that group of data is just the chunk of data. Each one should have the primary key. Do you remember? The primary key is one of the most important, the constraint, the modeling constraint in the relational database model. So we are fighting with such a redundant data. So in the chapter, so we are going to talk about how make the database design the better. So title is functional dependency and normalization for relational database. So this is the format, the way to make the title of this chapter. In other words, how can we make our database design better? That's our first goal of this chapter. So how can we make, what is a good database? So good database design. In other words, no redundant the data. So our goal is to eliminate any redundant information. When we are talking about such a redundancy not only just ID, but also semantically, the no redundant information. So when we talk about the goodness measure or how much good database design is, in other words, we try to eliminate such a redundant information as much as possible. We cannot eliminate all redundancy, okay? As much as possible. So formal way to conduct such a process is there are two. I'd like to introduce two different ways. How can we make the database better or the good? So one is informal way. So another one is the formal way. So think about what is the meaning of a formal? Formal dress. The formal. Proper. Dignified. Formal in computer science. Standardized. How can make the algorithm data standardized? Using what? Whatever. Mathematics. Okay? So when we talk about in the science and engineering and such area, when we talk about the formal definition or formal processing, formal discussion, formal means using mathematics. That is the standard, that is the perfect. Okay? So that is the reason if you have a new idea of the indexing. So I have new idea of the indexing algorithm that it will be faster than the B+3, 10%. How can you prove your idea? mathematics. So if you can prove your idea by using mathematics, that's done. You don't have to implement. You don't have to test. You don't have to do the experiment because mathematics is a perfect. However, not always such a mathematical proof, formal proof is possible. So, especially in computer, depending on computer is the data is not infinite. Our data is finite. So, but in mathematics, we consider the data is infinity. Like think about the complexity analysis. Do you remember the big O notation, complexity, the analysis? So which one is faster? So and x plus to the power of 8, and d is x squared. Which one is faster? This one is faster. Even though we have bunch of number, we don't care. We are going to consider degree. Okay? The degree of the highest degree of the factor. Why? The x is infinity. Eventually this one will catch up to this. Okay? So when we talk about the format, it's basically considered the infinity. Any case, it should be true. And also not always easy to understand. Also sometimes not easy to express your idea using mathematical equations. So in computer science, so we are dealing with a finite data set and the finite, and also our performance depends on what? Computer power and the other factor. There are a bunch of. So sometimes we can use, most of the time, simulation. We can use the simulator and the simulation or entire implementation. So to prove the idea. So there are two different ways to talk about the goodness measure of the database design. Informal way, formal way, both of them are focusing on what? No redundant information. So informal way first. Informal way. So there are several guidelines. So first guideline. The first guideline is, it's a simple. One table, how many semantic? How many meanings? When you create the one table, how many meanings are in a table? Just one. Nobody want to create the employee table that includes the student, employee, and any other. Only employee, right? Also think about your ER modeling. When you are doing ER modeling, we are going to find the entity, student entity. So Lee entity, James entity, and the Patel entity. Then by grouping, when you are doing group by what? You are thinking about, you are grouping for what? Only student. You don't want group teacher, right? During the ER modeling. So which means one table has one meaning. Because of that, so even though before you take this class, so when you are doing the project in web application or the Java, object-oriented, the programming, OP, so some of you guys already use the database, SQL Server or MySQL. Then, how do you create the table? You can just create the table, like the customer table, item table, and transaction table, and what else? The payment table. How? Even though without taking this class. Because intuitively, we know one table, one meaning. So, think about your room. So when you clean up, organize your room, nobody wants to put all the clothes, like the underwear, or the winter, or the hot pants, short pants, whatever, put in the one drawer. No, you want classify. So spring, summer, winter, and fall, and jacket, and you are going to group it, right? That's a kind of natural, the intuition. Same thing. So when we organize the data design, one table, one meaning. Because of that, we can actually create the table without understanding this. Not always in general. This is an informal way. Okay. Second guideline is it's just informal way. How can make our database design is better? Second guideline is, let me give the one example of the database design. So this is called the EMPDEPT table. Forget about the first one, but this is the database design for the employee ID, DNO, EMP name, D name, and the work hour, like that. The primary key is this one. If we consider this guideline, is this good database design or bad database design? Definitely bad, because this EMP-DPT table has one. Employee, one meaning, and the department, another meaning. So even according to this first guideline, so this is not good. Forget about the first guideline. Let's consider this one. So we may have the employee ID 111, DNO1, and name is Lee, and the D name is HR. And number of hours, I'm working on 40 hours. And 112 has the department number 1, and employee. That's it. The department number 2, James, and it's IT. 10 hours. And 113, and 2, and who else? The Pater, and the IT, and the 20 hours, like that. So let's say I'm the only one in HR department. I'm the only one in HR department. So what if I quit my job? We can delete the data, right? Then what happened? HR department will be deleted, which means this is not a good database design. This is called the anomaly, deletion anomaly. Okay. So if your database design is not a good database design, you may have such an anomaly. So this is an example of delete anomaly. When you delete data unexpectedly, some other meaning. HR should exist, even though I quit my job, but you can't. There is another type of anomaly, update anomaly. Update anomaly means, so let's see this. We are going to decide the name of the IT department from IT to technical support. So technical support. Even though how many departments you are going to change? One department. What about the database? You need to change all of them because it's not a good database design. Some duplication. So this is called the update anomaly. There's another one, insert anomaly. Insert anomaly. I'd like to hire the new employee who is not assigned any department, but because of a missing department, we cannot insert the data. Okay? So this is called the insert anomaly. So if your database does not have such an anomaly, which means it's a good database design. So second guideline is avoid any the anomaly situation. Insert, delete, update. Okay. Two more guideline. So third guideline is called the as less null as possible. What does that mean? Null. So do you think null is good or not? What is the null? Null means no value. Not exist, like the host. Okay? You cannot count such a null. Then why do we keep the null data? in a database.
Sometimes you have to.
We have to why? Do you remember why we need the null? It's used in the database for a sign.
Because sometimes you don't want to have a true or false value. Sometimes you just have unknown.
Then what is such a time? It's from the database design. So go back to ER model. When we design the student entity type. So what is the entity type? It's a common information. Name, ID, major, and the phone number. So he's a student, name, ID, address, phone number. Name, ID, address, phone number. But he doesn't have a phone number. He cannot be part of the student entity type. It's not fair, right? He doesn't have only the phone number. So instead, why don't we use the null in case any missing data? Because our goal of this design, student entity type, is what? Standardization. Standardized to what? Name, ID, address, and phone number. If he doesn't have phone number, he cannot be. So to address that, so we can use the null. So how can you represent the null in our computer system? Null doesn't exist. So just ignore? No, computer cannot understand the existing or not existing. Anyway, we need to use something value. So anyone who learned the C program language? In C, how can you represent the string?
It's an array
Array of
of characters.
character.
Followed by the null character.
That is a null character. Null character means to specify end of string, because we don't know where is the end of array. So we can use such a null. This doesn't mean the null used in the database. Instead, this one point end of a string without any meaning. Okay? At the time, the reason why we select the null pointer in the string of C is it's not frequently used. So we can use any data structure, internal data structure, which is not, or in other words, which is rarely used, something valid, like this is story up to DBMS design. Okay? Rarely used one will be used, which means if you have many null, waste of space. Okay? Also, if you have, for example, all data are null for the phone number, nobody has the old phone number, then we don't have to have such a column. It's a waste of space, right? So, which means when you design the database as less null as possible. You cannot avoid the null-free database design, okay? But instead, as less null as possible. Not only because of the capacity, the waste of space, but also it will be it will hurt performance. Okay, so as less null as possible. So first guideline, one table, one meaning. Second guideline, so it's to avoid any the anomaly situation when you insert or update the data. Third one, as less null as possible. Fourth, when you design, when you pursue good database design. The last one is any unexpected or the superiors the data when you join. So let me show you the one example of the such a case. So this is the, let's say without considering guide 1, 2, 3, so we have the two tables. So initial database design. One is employee underscore location. It has the e-name and key location as a primary key. And the other one is employee underscore the project one. Social security number and the P number. P number and hour is the primary key. And the P name and P location like that. We have two tables. So we are going to join the two tables. So forget about whether this is good or not. Based on this, definitely not, because it has the two different meaning, and this one has also two different meaning. This is not good based on the first guideline. But let's accept that this one is the initial database design. Then what we want to do from the two tables is we try to join two tables. Okay? What can be used for the join the condition? We can use P location and the P location. These are the common, the column. So if we join these two tables, what happens? So its output is like this. So P location is used, then to join the first table, and the second table is the first table, and the second table will be joined like this. However, if you see the sum of the data, like the social security number 1, 2, 3, 4, 5, 6, 7, 8, 9, and this one is not the Joyce who, Joyce who is the chair of the department. Joyce the English. Actually, the 1 through 9 should be the John Smith, but when we join these two tables, like the Belair is Belair, Belair is another Belair. Okay, we can join, but John B. Smith should be the 1, 2, 3, 4, 5, 6, 7, 8, 9. But when you join this one, it's a 4, 5, 3, 4, 5, 3, 4, 5, 3. Why this one happened? This database is not good. Okay, this one is not a good database design because it has a lot of redundant information. This is one extreme case. Nobody will do such the database design, but this is one of the examples. Sometimes you may not realize, but when you join, it produces unexpected data. So this one is unexpected data, like this one, and the SRS, third one is not our expectation. So this one is called the spurious tuple or the unexpected data. So that last guideline is when you join two tables, you do not have such unexpected data. So this is just informal guideline. It's not very complicated, mostly straightforward. You already know when you are doing the database design. So because of that, even before you take this class, you are able to create a simple database. Like the customer has one meaning, and department, and the transaction, item, and so on. So this is a informal guideline. However, that's not enough. In case it's more complicated, it's good intuitively to understand, but it's not the perfect. So we are going to see such a formal guideline, formal way. The second approach is formal way for the good database design. Okay, that is called the functional dependency. So functional dependency. What we are doing is we try to make the database design good. Good means what? No redundant information. So which means, think about how can we represent such an idea of database design in mathematics. So how can we represent the one meaning using database as the mathematical equation? It's not that simple. It's a really high level. But long time ago, so several researchers from the Berkeley, the Stanford University, so including one of the PhD member, Dr. Emma Suri, they tried to find the mathematical way to cover this idea. No redundant information, no avoid such a thing. At that time, key part is how to represent the one meaning of the data, meaning semantically. So when we are talking about the meaning, we understand in our mind, right? The employee is only employee, and department is department. But mathematical equation, they cannot understand which one is employee, which one is the department. So any way to represent such idea? So at the time they adapt this one, function. So do you remember, why don't we go back to the, I think the 5th grade, 6th grade, the introductory algebra class? Do you remember this? So in other words, f of x is, for example, 2x. What does that mean?
Y is a function of x.
It's a range, a domain. Domain or range? X is domain, and 2x is the range, right? So it depends on x. If there 1, output is 2x, right? Output is determined by what? Input, okay? If we have the input, we know the output. So y is determined by x. Depending on x, we can find the y. This is a function. So when I learned the function first time, it looks like the black box. We don't have to know about the inside. Input is 2, output is 4. Input is 4, output is 8. So input is x, output is 2x like that. So then we can say that in graph notation, y equal 2x, and the functional notation, f of x is 2x. So this is a function. So function is very, very useful to simplify the relationship between x and y, domain and range, like that. Okay? So we are going to use this idea to find the meaning of the table. So for example, so when we have the employee ID and the email and the DM and the phone number, like this. So attribute of what? Employee. However, not all each and every attribute are the same. If we see closely, if we know the employee ID, we can identify the email, right? And also, if we know the employee ID, we can identify department number where this employee is working, right? And also, employee, if we know the employee ID, then we can find the phone number of that employee. However, if we know the DNO, can I find the employee phone number? No, we cannot do that. Or if we know the email, can I identify the employee ID? Sometimes we may have the common name of the employee, so we cannot. So we can classify the attribute two parts. One is if we know the employee ID, if we know the X, this one, we can determine the other attribute. So at this time, we can write this way, employee ID. Determine what? E-name, DNO, phone number. A group of attributes can determine another group of attributes. So this one is called the functional dependency. Functionally, attributes are determined by another attribute. So, in other words, a group of attribute X determine another group of the attribute. So this is called the functional dependency. Why this one is important? This group of attribute. So functional dependency actually define one meaning. In this case, employee. What if the previous example? So bad example. Let's take a look at the bad example. So here. So social security number determine email. Social security number determine the bill. Social security number determine address. Social security number determine the number where this employee is working. However, social security number determine research Social security number determine manager. Actually, this D name and D manager is determined by what? D number. So we can find the two functional dependency. One is F1 is the employee SSN determine the E name, B date, address, and another group of attribute that is the D NO. D number determine D name and D manager social security number. So we can identify two functional dependency from this database design, which means this is good or bad. This is bad. We need to separate them because we want one meaning, one table. But here, meaning is actually implemented by using functional dependency. So functional dependency is a tool, mathematical tool, to identify the meaning of the data. So what is a functional dependency? A group of attributes determine another group of attributes. Question. So we now understand what is a functional dependency. How many functional dependency can you find from here? Not here, the simple one. Here. How many functional dependency can you find? How many? One. Actually, really a lot. So let's see that this one is one example. So this one is one example of functional dependency. What about this one? Employee ID plus E name. Determine DN. Is it okay or not? That works. Anyway, employee ID determine this. So even though you add the E name, this employee ID plus E name determine DN. What about this one? Employee ID plus phone number determine E name. We can make as many functional dependency as possible. So what we want is not this, right? What we want to do is minimal part of the X side. Okay, minimal. So this one is called minimal functional dependency. So what we want to find from the database design is minimal functional dependency. Minimal means, what is a minimal? So nowadays kind of trend, the minimal life. The minimal life, so you don't want to buy anything instead only the need for your life, right? So without that item, you cannot live, you cannot survive. That's a minimum, right? But for drink, it's not part of a minimum, right? So you can always take out such an additional thing. So it's exactly the same thing. If you take out this, there exists a functional dependency. So you can take out. So if we take out the phone number, still there exists a functional dependency. However, if you take out the employee ID, what happens? You lose the meaning of this functional dependency. So that is called the minimal functional dependency. Actually, there is a way of finding minimal functional dependency, okay? But I'm not going to explain using the mathematical proof. So it takes a couple of weeks to understand everything. But this one is from the set theory. So if you are very interested in the set and the set theory, it's worthwhile to read the book. It's a freshman or sophomore level, the mathematics department. So you will see the proof of such a thing, but I'm going to skip this part. So instead, idea of the minimal, so what we want to do, what we want to find from the database design is minimal functional dependency. Okay? From now on, even though I'm saying functional, why don't you please find the functional dependency means minimal functional dependency. So do not argue. So after the final exam, this one can be yes, that's true. But from now on, when I'm saying the functional dependency, that means minimal functional dependency. So what we want to do is find the first minimal functional dependency. Why minimal functional dependency? That represents meaning of the data. Okay. Then the problem is, what if we find any redundant data? So we can find the redundant data, something problem based on guideline. Also, we can find ideally how many minimal functional dependency per table? 1. So what if I found the 2, 3 multiple functional dependency? Then
Split them up.
yes, that is the only solution from now on. So our goal is to make the database design good, better. Okay? That means no redundancy and the one functional dependency. So if there exists the redundant information, or if there are multiple functional dependency, what will be the solution? It's a split. Then, or it's a segment. Sometimes solution is segmentation. Always segment. Segment by what? Meaning. Segment by functional dependency. So it's a simple idea. It's a simple processing to make our database design is better. That processing. So if you find any redundant information or if you find any multiple functional dependency, we are going to segment or split them up. That process is called normalization. So normalize. So from now on, we are going to see how to normalize the data. Normalization means, have you ever heard about the database normalization? Anyone? So normalization, what is in general normalization means? Normalize. In general, not in the database. When you in statistics or just normalize. So you probably use a lot of time in science class or another math class. So why don't you normalize? Normalize means, so think about your grade. So some of the, so I usually scale the 1 to 10 for quiz and for handout, homework. Is it really the same way? No, we need to normalize. Okay? Normalization means standardization. It's a standard. Right? That should be fair. So when we talk about the normalization in the database, that means segmentation here. So we are going to call it a normalization process. Normalization process means we are going to make the database standardized. Standardization means no redundant information, no redundant data. Okay. There are different levels of normalization. It's simple. If database is not normalized, it's called the zero or unnormalization form. So what is the unnormalization form means? Example. Unnormalized.
It's always unique. It's not standardized.
So redundant or no redundant? A lot redundant, like your room. If you do not organize your room, put everything. So new homework, new clothes, old one, just put everything on your bed. That is unnormalized. Okay? Which is not good. So sometimes unnormalization form means bag of data. It's just a bunch of data. Okay? Not the standardized. So always start from the unnormalization form. But if you normalize a little bit, so when you clean up your room, first you are going to classify, normalize by use. Okay? So needed one, or garbage. Then you can throw out the garbage, like that. So first normal form, there is a first normal form. If you normalize a little bit more, second normal form. If you normalize more, it's called the third normal form. What is the next? Actually, BCNF. Then fourth, fifth, like this. So, which means this one is most standardized, normalized. Most normalized means high redundancy or low redundancy. Low redundancy. So, zero normal form means it's a high, it's a standardized or non-standardized. It's not standardized, which means high redundancy. So our goal is to go into the higher normalization form. No redundancy. Then we will check step by step. Step by step. First, good news. We don't have to cover each and every one. We are going to cover up to BCNF. Because this one is very, very rare. Okay? Even I never seen the fifth normal form case like that. So up to the BCNF cover 99% of the database design. So you probably will be asked later when you join the project. Your project manager asks, why don't you normalize the database design, because you already took the database design. That means up to BCNF. Another good news. Even though I'm going to explain how to do this one from this. Before that. So if you already found the BCNF normalized form. BCNF means automatically third, second, first is already satisfied. If you already find the third normal form, database design, it's already second, first, but not BCNF yet. You can do the only BCNF. So this is another good news. You don't have to do each and everything. Also, third good news is, this is the same, generally saying that if you believe you have the normal average intelligence level. So what is the way of measuring the intelligence level? IQ. So what is the average of IQ? 100? I heard that it's less than 100 on average. But anyway, I believe you are above standard in terms of intelligence level. If you believe you are a normal person, anyone can do the automatically third normal form. Okay? Even though we are going to discuss each and every one, because it's class, but if you believe you are the normal person, you can do the normal. Why? Because the third normal form later you will see. So we already saw this kind of guideline. Okay, guideline will be described in this normal form. But nobody wants to mix the database class, the material database class with the other data class. So you can file only database. You want to file only big data course. You want to file AI class like that. Nobody wants to mix up, right? So even though you never thought about such a normalization, you want to group by the subject or context. That is the level of third normalization form. Because of that, before you take this class, some of you guys already create a table using MySQL. Okay? And also you can take the what? Customer table, item table, transaction table, and payment table, like that. So that is third normal. So, but BCNF is slightly different. So it's a little bit, it's non-intuitive. So we need to think about. So we will see each and every level of the normalization form up to BCNF today, hopefully. So how many minutes? So 20 minutes, maybe enough. Okay. Let me quickly go over up to that part. So we try to measure the quality of the database. Simply, there's no redundancy. So we try to find the database design without redundancy. So first guideline is one meaning, one tuple. So we wanna design database explain the relation by relation. Okay, one relation, one table has one meaning. And second guideline is no insert, no delete, no modification anomaly. Okay, that is the second guideline. And third guideline is the as less null as possible. So you cannot have the null-free database design. It's an ideal case. So as less null as possible. The first guideline is no spurious tuple. In other words, no unexpected data when you join. Okay, this is the informal guideline. So formally, using the mathematics, we try to prove idea of the normalization using what? Functional dependency. So functional dependency will be used for the measure of the fitness, which means one functional dependency is the best for table. So when we talk about the functional dependency, should be minimal functional dependency. Left-hand side only the minimal attribute. The other attribute. At this time, so this attribute, left-hand side attribute is called the prime attribute. Prime, important. The other attribute is called non-prime. Okay? So there are two kinds of attributes, prime and non-prime. So we are going to use the prime attribute. So for what? Normalization process. Okay? So we will see each and every step. So that is a functional dependency. There is a way, mathematical way, formal way to find the minimal functional dependency, which is described here. Okay, minimal functional dependency. But I'm going to skip this part. So if you are interested to know about the formal way of the how to find the minimal functional dependency, read the textbook. Textbook described very detailed. Because the author of the textbook, Dr. Elmasari, he actually his dissertation, PhD dissertation topic was a conceptual design, including this part. So there is an algorithm, so you can find. I don't think other textbook introduced this one, only our textbook. But I'm going to skip this part. I tried to cover this part. So several years before, it takes 2-3 weeks, but nobody understands. But I don't think you need such a formal way. But those who are interested in the PhD level research on you don't have to do the exactly same thing. But who knows? I have a new conceptual design, the idea. At that time, you can use such a way. Okay, so we are going to use the normalization. Normalization means it's a standardization using functional dependency and the prime attribute. We are going to standardize. How can we standardize? Keep in mind, splitter or segmentation. That's the only solution. We are not going to add up. Then instead, chop by what? At the time, depending on how to segment, we have a different level of normalization. Our goal is up to BCNF. When we are saying the first NF, first normalization form, second normalization form, third normalization form, BC means Bosch code. Bosch code is you remember the name of code, Dr. E.F. code, who provides a relational model, and Bosch is his colleague. They found the something redundancy, unusual the redundancy. So that case is called the BCNF. It happened in our real data. And also, Dr. E.F. Elmasari, the author of this textbook, he worked together with them at the time. Okay, so normalization, we already talked about. Later, I will introduce the denormalization. Okay. Denormalization, as you can expect, is the opposite way. Opposite way. Okay. So which means combine together. So redundancy. We allow redundancy sometimes intentionally or purposely. Later we will see. Okay, so super key. So what we are interested in the key, because key determine non-key. Prime attribute determine non-prime attribute. At the time, super key is any set of key, as we have seen, employee ID plus e-name, employee ID plus phone number. So what we want to do is the minimal super key. That is called a key. Okay? How many keys in database in general? At least one. It can be more. Okay, 2, 3, multiple keys are possible. However, how many primary keys? One per table. You need to select one of them as a primary key. The others are called the candidate key. They are almost the same as primary key. It was candidate but not selected. So, however, still candidate key keep the same property like a unique. So, if an attribute is unique, we can use search because it's unique. So example is like the employee table. Employee ID is a unique key. Social security number is a unique. It's also key. So we can select the one of them as a primary key. The other will be the candidate key. So if attribute, in other words, left-hand side, if the key attribute belongs to either primary key or secondary key, which means the candidate key is called a prime attribute. That makes sense. It's a prime attribute. The others, non-prime attributes. So when we are doing the normalization process, we need to decide the rule to segment to remove the redundancy. At that time, we are going to consider the functional dependency as well as the prime attribute. Okay? So prime, keep in mind, what is a prime attribute? What are the non-prime attributes? Finally, first normal form. We can start from the zero normalization form, unnormalization form, or back. So there's no standardized, only the back of data. So first normal form is, if you go back to the relational database model, again, relational database model, there are several rules for modeling. The constraint. One of them, do you remember, is the atomic value. Atomic value. No table inside the table. Table inside the table is not available. So only one value, atomic. Do you remember that? Because of that multi-valued, it's not allowed in relational database. So also relational database does not allow table inside a table, which is very popular in object-oriented concept. Nowadays, most of the program languages, they support data structure inside the data structure, list inside the list. List can be used as part of the dictionary, and the object inside object. So it's totally fine, except the relational database model. Relational database model does not allow the nested relation. Also, no composite. Composite means address, for example. Address has, in ER modeling, address has street number, street name, the zip code, CD name, state name, like that. This is a composite attribute. But when we create the relational database, we cannot have this one. Instead, one by one in total. So this is a atomic. Then definitely multi-value. So first normal form, focus on attribute level. No composite, no multi-value, no nested. In one word, what are they? How can you explain in one word. One word. So first normal form. The first normal form is one word. Atomic value. Okay, one value. Atomic value is the first normal form. So how can you check whether my database is the first normal form or not? Check each and every attribute, whether atomic or not. So let's see the example of that. A. Is it the first normal form or not? The first one, the department. So what is the first normal form? Atomic. Each and every attribute should be atomic value. In other words, no composite, no multi-value, no nested. D name, atomic. D number, atomic. D9 intersociation key number, atomic. D locations is a multi-value. So this is not first normal form. What about B? Atomic, but it's a multi-value. So this is not the first normal form. What about this one? D name, atomic. D number, atomic. Manager social security number, atomic. D location is the atomic. So this is the first normal form. How can you make this unnormalization form to the first normal form? Decompose. Decomposed by the value. That is this one. You can see the Bel and Sugarland and Houston. Okay? But the key is changing. D number plus D location. This is the first normalization form. So this one is the first normal form. I know this one still has a redundancy, like the 555 research. But first normal form, normalization form is not directly jump into the perfect one. Actually, ideally, the perfect normalization form is zero redundancy, that is single attribute table. If you have the single attribute table, that is perfect. But we don't want to such a thing. So we need to make the step by step. So to make the first normal form, we can decompose by the value. In case of composite, we can decompose by the attribute. And in case of multi-value, decompose by the value. In case of nested, we can take out the nested one. So that is the first normal form. This is an example of the nested. You can see the inside, the John D. Smith has the two projects, project 1, project 2 like that. And Joyce English has the two projects like this. So this is not first normal form, okay? Because it's a nested table inside the table. So how can we make the first normal form? Decompose this part, nested. So we have the employee information. Then this one is the project information. So we can take the project information. So like this one, social security number determine E name. This is one. And another one is social security number plus P number determine hours. So we have another decomposed table. So question, is this the first normal form? You can check each and every attribute at atomic. So yes, this is the first normal form. So first normal form, check the attribute by attribute, whether it's an atomic or not. Question, so simple. Okay, not complicated. You can check the only attribute. Then next, second normal form. So second normal form, first I'm going to explain what is the second normal form. For key dependence. Whole key dependency. Meaning is, let's see the example of that. So, our initial database design like the employee EMP underscore project. And the primary key is social security number plus P number. And we identify hours, E-name, P location. Okay? This is our initial database design. We are not sure yet whether if this is the good or bad. We are going to check. So first, is this the first normal form or not?
I'm not sure about P location.
There's no plural. It's a singular. If this one is a singular, it's atomic. Hours does not mean number of hours. Okay, so it has the 10, 20 like that. Okay, so this one is first normal form. Then second normal form means it's a whole key dependency. So first we are going to find the functional dependency. We can find social security number, P number determine hours. This is one functional dependency. Then social security number determine E-name, another functional dependency. So this one is the third one. P number determine P name and P location. How many functional dependency? I'm saying minimal functional dependency. Okay, how many minimal functional dependency here? So FD1, FD2, FD3. How many different meanings? 3. FD1, FD2, and FD3. Is it good or bad? It's bad. Why? Because we expect attribute determined by the whole key. What is the whole key? Social security number plus P number. But inside there exists FD2. E-name only determined by social security number. It's a partial dependency. Right? It's a partially depend. And also P name and P location is determined by what? P number only. It's a partially depend. So whole key dependency is different from the partial dependency. Okay? Because FD1 is the meaning of what? Work. Right? And FD2 is the meaning of what? Employee. Right? FD3 is the meaning of what? Project. There are three different meanings. Why? Because it has the partial dependency. So what will be the solution? How can we make the whole key dependency? Decompose. Decompose by what? Meaning is, in this case, dependency, functional dependency. So we can take out FD2, social security number determine E-name, FD3, P number determine P name and the P location. Okay? Then the original one is social security number plus P number determine hours. So is this are they second normalization form? Prime, non-prime. Okay? So non-prime determined by whole key. Yes. E-name determined by social security number, whole key. And P location determined by whole key. P name determined by whole key. So this is the second normal form. So second normal form is simple, whether whole key dependency or not. Be careful if you have a single primary key, single attribute primary key, single attribute primary key, which means how many prime attribute? One prime attribute. One prime attribute. Automatically, second normal form. Why? Why? You cannot have a partial key, right? Because it's a one attribute, one single attribute. You don't have any partial dependency. So in case single attribute primary key, single prime attribute, automatically second normal form. But this one you need to check. So it's determined by social security number plus P number, whole key dependency. Then it's a second normal form. However, this one we have the functional dependency, partially dependent. Partial functional dependency. We don't want partial dependency because it has a different meaning. Okay? So this is the second normal form. So what is the first normal form? Automy. What is the second normal form? Whole key. Okay? Then third one. Third is the, you heard about in inference rule. I think that in your math math. A determine B. And B determines C. Then can I say A determines C? In inference, the rule, this is true. A determines B and B determines C. We can say A determines C. We can apply this one into the the functional dependency. In functional dependency, this one is called transitive functional dependency. Transitive functional dependency. Let's see the example. So we have the initial database design. Social security number determine email. Social security number determine B-date. Social security number determine address. Okay. So this one is okay for the employee. Social security number determine D number. And also social security number determine D name, social security number determine D manager social security number. However, we can find another functional dependency. D name is determined by actually D number. Right? And D manager social security number determined by the D number. So we can identify one functional dependency and another sub-functional dependency, which means eventually social security number determines D number determines D name. This D name was actually originally determined by the D number. So how many functional dependencies? 2 functional dependencies. Even though this is a whole key dependency, this is the second normal form. How many? This is a primary. This is not primary key. Right? Primary key is a social security number and the single attribute is a whole key, automatically whole key dependency. It's a second normal form. But we have the sub-functional dependency. So if we have the 2 functional dependency, which means 2 meaning, it's a redundancy. So third normal form. Third normal form does not allow transitive. Does not allow transitive. In other words, nothing but key dependency. In other words, only key dependency. Only key dependency means the D name actually determined by what? Non-key. Right? So D name determined by the D number. D number is not a key. D number is another non-prime attribute. But in this case, we can find D name determined by the D number, D manager social security number determined by the this one. So third normal form does not allow such a transitive. Solution? Decompose always. By what? Dependency. Functional dependency. So we can take out this. Employ SSN, oh, it's a mistake. SSN determine name, B-date, address, and the D number. Another table is D number, determine D name, and the D manager social security number. So this is a question. Is it the third normal form or not? Yes, there's no sub-functional dependency, only one functional dependency. So it's the third normal form. If this one is a third normal form, automatically second normal form and first normal form. So this is the up to third normal form. So third normal form is no transitive functional dependency. In other words, nothing but key. So only key dependency. You can imagine if you have one primary key and one functional dependency. It's a third normal form. That makes sense. As I said, that if you believe you are normal person, so nobody wants to mix the word the transitive or the complicated. Just a simple primary key, main idea, and other description. So that is the reason automatically you can do the third normal form. So this is the third normal form. The last one today. Let me show you the one example first. So let's take a look at this case. So property ID determine country name, the lot number, area. So this FT2 is a country name, lot number determine property ID, area. So country name and lot number is the prime number. So we can decompose this. Lot number, property ID determine area, and the lot number. Lot, another one is area determine this. No, not this one. So this. Right. I think we do better because what time? So already. We need a little bit time to introduce idea of the BCNF. So keep in mind, normalization form is based on the functional dependency as well as the prime and non-prime entity. First normal form, check the attribute, whether atomic one. Second normal form, whole key dependency. In case a single attribute, primarily or numerically second normal form. Third normal form, no sub, no transitive. Okay, so that is the normalization. We will see the BCNF next class, and I will show some example of the normalization. That will be the part of your also the project. You can normalize if you need. Any questions? Okay, thank you, and we will see Wednesday.